Welcome back. So you're in a course on machine learning with Python 3 conducted by Subburaj Academy. You are in module 2, linear regression, the second module of the ML course. You are at lesson 9. It's about a case study for first initially with multiple linear regression with multiple features, then with single feature and linear regression. So in this case study, we'll see both simple linear regression as well as multiple linear regression. It contains both multiple linear regression as well as simple linear regression. The data is 50 startups. So before we look at that, you should know what the goodness of it measures. What is goodness of it? How well is the fitting? How well is the modeling? To evaluate the performance of machine learning model. So you make a model. So you have to look at the quality of the model. So you have to measure how measures to evaluate the quality. These measures assess, make an assessment how well the model fits the data. It can be used to compare different models. Okay, different model parameters. So you may have different parameters. Okay, so you try to find out which model is the best. So you can compare models. First, you can assess the quality of the modeling each time, and you can also use it for comparison. What are the measures? There are two measures, three measures. One is mean squared error, MSE. MSE measures the average of the squared differences between the predicted values and the actual. Suppose the predicted value is y pred, and actual value is y. Then y pred minus y whole square divided by the number of samples. That will give you MSE, mean squared error. You can also take a square root of MSE and you will get RMSE. Got it? R square is another measure, important measure, good measure. It measures the proportion of variation in the dependent variable that is explained by the independent variables in the model. So it's a good measure for many machine learning models. R square value of 1 indicates perfect fit. Very rare to get. I got once or twice. If it's 0, no fit. Okay? There's no relationship between the. And what are the measures? I told you 3 measures: MSE, RMSE, and R square. Then I expect you also how to do it. Usually you do MSE and R square. That's good enough. So now we will turn to Jupyter Notebook to look at the case study. As I told you, one is the multiple linear regression, the other is simple linear regression. So this is Jupyter Notebook. So what we do initially, import the libraries numpy, import numpy as np, import matplotlib.pyplot as plt, and import pandas as pd. So then you have the data set, which is 50 startups. That is the pd.ddcsv and 50 startups. So data set is the data frame, and name of the file is 50 startups. And you can print the first 5 rows of the data set by saying dataset.head. The first 5 rows: R&D spend, administration spend, marketing spend. These are 50 startups, okay? And the state in which they are located and the profit. So obviously profit is the response variable, and other columns are the features. So now we are going to take data set I log. X is 0 to 4. 0, 1, 2, 3, 4. And y is the fourth column. X is all values of at column 0 to 3, because 4 minus 1 always. The single value means that column. So y is all values at column 4. You can print first 5 values of x and y also. So you get the first first 10 elements of x. No, before that, yeah. The first 5 columns, see, the one row, and xy and y is the profit. The response variable is in the last row. The other 5 rows, first 5 rows, represents the features of the 50 startups, the first 5 rows. Got it? So New York also, see, there is something called the state. So the state cannot be used for regression. So we have to encode them into numbers. Got it? If you want to use it. If you don't want to use it, fine. If you think the state matters, then you have to convert them into numbers, 0, 1, 2, etc. So now we can do it by encoding categorical data. This is categorical data. Others are numbers. The categorical data is the last one. So we want to encode the data. So for voice, what we do is from sklearn.preprocessing, import a label encoder. Now we are going to do only label encoding, but when you import, you have to import both label encoder and one hot encoder. So label encoder X is label encoder. So it encodes. X, the third one, 0, 1, 2, 3. That's the one we have to encode it. So label encoder dot X fit transform 3 to 4 means the third one. Right? So that will be this whatever you encoded, that will be substituted in the third column. So after label encoding, you get this. See, the last one was New York is 2, California is 0, Florida is 1, and again New York 2. So what we have achieved is by encoding it, using label encoding it, we converted this, the last column, into numbers. I've done it. Okay. So after you are done, we are going to now do the linear regression. So we have encoded the third column. We assign x is all of them, and y is this. The first 5 rows. So now that we know the features of response variable, we can carry out linear regression, multiple linear regression, because there are 4 features. So naturally, multiple linear regression. So follow the steps. Import linear regression. You must import from linear model. Import linear regression. You need to cover the metrics. So import means squared error, and R2 square. R2 square means R square. So we won't need both MSE and R square for evaluating the goodness of our model. So we have to divide this data set into two pieces. Test a training data set with which we will train the model, and test data set with which we will predict how good is the fitting. So import numpy as np. So assume x and y are independent variables respectively. Split the data set into training and testing sets. The testing is required to assess the quality of the model. So x train, x test. X train will be used for training, x test will be used for prediction. Y train will be used for training, corresponding y train. Each column, no? The corresponding values will be taken. And y test is the corresponds to the x test. So train test split x comma y. Test size is 0.2. It means we will use 80% of the data as training set randomly and 20% as test set. Then we do feature scaling. You must do in every machine learning modeling. You should do feature scaling. What does it do? It reduces the features into numbers, very small numbers, say -1 to +1. So for this purpose, what you do is import standard scalar and SCX standard scalar. X train SCX only the X will carry out feature scale, not Y. You should not touch Y. The X train X is both we are carrying out feature scaling. Then elements of X train after scaling, we print the X train. Then elements of X test after scaling also. Now we come to the crux for the problem. Create a linear regression object. Rig is equal to linear regression. So we have rig is an object, and that will call linear regression. Fit the model. Rig dot fit Extend Y. So you train the model. You want to train the model, you need extend and Y train. And predict the value of Y using model and the training data. Y train prediction is equal to predict X train. Similarly, X test Y test prediction also. See, I mean, we can predict both. We already modeled it, but still you can predict what will be the Y train values with the new model. Similarly, X test prediction is predict X test. So both Y train prediction and Y test predictions are available. So you can calculate MSE for both training as well as testing. So MSE train is mean squared error, Y train minus and Y train prediction. MSE test similarly mean squared error, Y test prediction. Similarly, you find out R square for both training as well as testing. And you can put the results. Okay. Now we can run this code. Very interesting, isn't it? Okay, run it. So, plot.show will show the plot. This is how it works. All the 4 okay, yeah. So excess of standard scaling is this, and what the results you get, MSE for training set, data set is so. The X test and Y test were listing right. We are listing it. Here we are listing printing X train, X test. So the X train, see the values are small, and X test after standard scaling, and MSE for training set we get those own numbers, and test data set we get almost closer. High. R square is 0.95, R square of test is 0.9. So we got all the measures. So intercept coefficients, you can get all the, because you always say y is equal to theta naught x naught plus theta 1 x1 plus theta 2 x3 x2 plus theta 3 x3. So you have 4 features. So theta naught is this, theta 1 is this, first one, theta 2, theta 3, and theta 3. Yeah. So all the coefficients also you can get. How did we get this? We are printing the coefficients. Intercept also printed, and look at coefficients also. We can simply print coefficient and record. So this model you can use it for with other data and other problems. And intercept is big intercept. That's all. R square to R2 test, R2 train, MSE. So we got everything. Good. And you can also plot it. Plotting predicted and actual values in the scatter plot. Y predicted that predict X plot scatter. And these are labeled actual values, predicted values. And the title of the slide is title of the multiple linear regression. And you can plot.show will tell you the plot. So actual values, predicted values, and this is the title of the slide. Now we are going to repeat it with one feature, means it becomes not a multiple linear regression, it is a simple linear regression. Which column are you taking? Your column 0. What is column 0? Column 0 is, look there, column 0, we are taking for only one feature we are taking, that is R&D spend. And column 4 is the profit. So we are now going to carry out a simple linear regression between R&D spend and the profit, right? So in the same case study, we are doing both the multiple linear regression as well as a simple linear regression. So that's repeating with one feature. The other things are same. Only 0th column will be X and the 4th column will be Y and all this. So we are also printing, see, think that there's only one data here, only one column. This is Y and this is X. Feature, response variable. Now we can do the same thing in the repeat of the same thing. So repeat of the same old code, so I'm not going to explain now. In the same program. So run it. So this is extend after some, after fixed scaling. The MSE is point very high, and MSE for training data set, MSE for test data set, R square little improvement, 0.94 for training and 0.92 for test. So it has improved with the single. I mean, some of the other features are not contributing to the modeling, okay, and also the coefficient process is found. That is, here it is theta naught, this is theta naught plus theta 1 x1, this is theta 1, right? So theta naught plus theta 1 x1. So the coefficients also we got it, right? So in the same case study, I converted the same program into simple, and you can also plot it. So you get this. So this will be better than the multiple integration. Got it? So this is the case study of a data set 50 startups. First we do carry out multiple integration with all the 1, 2, 3, 4 features, and finally we do only simple integration with R&D spend and profit. Okay, I hope you understood it. Please go through the slides and the program and carry out in your notebook. Only that will make you confident. Okay, that's all for now. Until we meet again. Bye bye.